Io looks like something pulled straight from the darkest corners of human imagination. Its surface is a chaotic tapestry of sulfurous plains, towering volcanic plumes, and vast, glowing lakes of molten rock that never seem to rest. But Io is far from a myth. It is a violent reality orbiting just over 400,000 kilometers from Jupiter. Caught in a relentless gravitational tug-of-war between the gas giant and its sibling moons, Io is physically stretched and squeezed. This tidal heating creates a world in a constant state of flux, where the landscape is reshaped by volcanic eruptions faster than almost anywhere else in the known universe. Io has consistently challenged our fundamental understanding of planetary science, provided the key to measuring the speed of light, and left us with questions that still echo through the halls of modern physics. As we look toward the outer reaches of our solar system and beyond, this restless moon offers critical lessons on where life might or might not exist. Let us begin a journey into the heart of a world that never sleeps. It is a long story, so let us start with the dreams of the past. Before we dive in, remember to like and share. In January of 1610, under the clear and silent skies of Padua, Italy, Galileo Galilei stood on his rooftop, peering through a telescope he had built with his own hands. By modern standards, it was a modest instrument, a simple tube with glass lenses, but it was enough to open a door that had been locked since the dawn of humanity. That winter, with a steady hand and a keen eye, Galileo pointed his telescope toward Jupiter. What he saw would forever shatter our perception of the cosmos. He noticed several tiny points of light near the planet, initially mistaking them for distant stars that just happened to be in the same line of sight. However, as he watched night after night, he realized they were moving in a way that stars never do. They remained close to Jupiter, changing their relative positions and occasionally disappearing behind the planet only to reappear on the other side. Galileo sketched these observations in his notebook, capturing a pattern that defied the prevailing wisdom of his era. These lights were not orbiting the Earth, they were orbiting Jupiter. This discovery of the Galilean moons Io, Europa, Ganymede, and Callisto was a revelation that shook the foundations of European thought. At the time, the dominant view held that the Earth was the fixed center of the universe, and that all celestial bodies moved around us in perfect circles. Galileo's evidence was undeniable. Here was proof that not everything revolved around our world. These moons followed Jupiter, indifferent to Earth's position. This raised a dangerous question: if Jupiter had its own system, why couldn't other planets? Why couldn't the Earth itself revolve around the Sun? Despite the risks of challenging the Church and the established Aristotelian philosophy, Galileo published his findings in a small book titled The Starry Messenger. The book sent shockwaves across the continent, sparking fierce debates among scientists and theologians. While some dismissed his work, others built their own telescopes to see the truth for themselves. Those tiny, featureless points of light carried a heavy significance, slowly eroding the geocentric belief system and hinting at a vast universe filled with other centers and other possibilities. The naming of these moons was a story of politics as much as science. Galileo initially called them the Medicean stars to win the favor of the powerful Medici family in Florence, hoping to secure a position as a court mathematician. For a time, this political name persisted, but it failed to describe the nature of these worlds. Other astronomers, like Johannes Kepler, argued that they were not stars at all, but moons or satellites. Eventually, the names we use today were proposed by a German astronomer named Simon Marius, who claimed to have discovered them around the same time as Galileo. Marius drew from Greek mythology, naming the moons after the lovers of Zeus, Io, Europa, Ganymede, and Callisto. Although Galileo initially rejected these names out of spite, the mythological framework eventually won out because of its consistency with the rest of the solar system. The name Io, referring to a priestess who was transformed and forced to wander the earth, feels strangely appropriate for a world defined by constant geological upheaval and motion. By the mid-17th century, Io transitioned from a mere point of light to a laboratory for fundamental physics. In 1676, a Danish astronomer named Ole Romer, working at the Paris Observatory, noticed a strange discrepancy while timing the eclipses of Io. He found that when Earth was moving toward Jupiter, Io's eclipses seemed to happen slightly earlier than predicted, and when Earth was moving away, they occurred later. Romer realized that the moon's orbit wasn't changing, rather, the light carrying the information of the eclipse took more or less time to reach Earth depending on the distance between the two planets. This was a revolutionary insight. At a time when most believed light traveled instantaneously, Romer used Io to prove that light has a finite speed. He successfully predicted that an upcoming eclipse would be delayed because of the increasing distance light had to travel, fundamentally changing our understanding of how information moves through the vacuum of space. By November, Romer's prediction was proven correct. The eclipse occurred exactly 10 minutes later than the earlier calculations had suggested. This was a landmark moment in scientific history, marking the first time anyone had used astronomical observations to prove that light does not travel instantaneously but has a finite, measurable speed. While the tools of the 17th century lacked the precision of modern instruments, Romer's estimate of the time light took to cross the diameter of Earth's orbit was remarkably close to what we know today. It was a revolutionary achievement that demonstrated how the regular, clock-like motion of a distant moon could be used to probe the fundamental laws of nature. Io acted as a natural cosmic chronometer, ticking steadily in the darkness of space. When that tick appeared early or late, it wasn't the moon that was faltering, it was the space between us that was changing. Later, other giants of physics like Christian Huygens built upon this foundation, using geometry and Romer's data to calculate a more direct value for the speed of light. For a long time following this discovery, Io remained a mystery, a blurry point of light that telescopes of the 18th and 19th centuries could not resolve into a world. It wasn't until the mid-20th century, with the advent of more advanced optical sensors, that the first hints of Io's strange nature began to emerge. Observers noticed that Io's brightness wasn't stable. It flickered and fluctuated in ways that couldn't be explained by simple shadows or solar reflections. At first, these inconsistencies were dismissed as atmospheric interference or equipment flaws. However, by the 1950s and 60s, Electronic light sensors confirmed that these variations were real. Some researchers began to suspect that Io's surface was not uniform, perhaps featuring patches of bright ice or dark rock that changed as the moon rotated. But without a close-up view, Io remained a mystery of a few pixels, until even stranger signals appeared, a faint, hazy glow sometimes seen around the moon's edge, suggesting the presence of an atmosphere or a cloud of particles that shouldn't have been there. The prevailing wisdom of the time assumed that small moons like Io were geologically dead, much like our own moon. Scientists expected them to be cold, cratered, and silent, as they lacked the mass to retain internal heat. Consequently, when infrared detectors in the early 70s revealed warm spots on Io's surface, the data was met with skepticism. It was only when radio telescopes began picking up intense, high-frequency energy bursts synchronized with Io's orbital position that it became clear something extraordinary was happening. There was a powerful interaction between Io and Jupiter's massive magnetic field. Theoretical physicists began to wonder if the immense gravity of Jupiter was stretching and squeezing Io like clay, creating internal friction and heat. This theory suggested that Io might not be a dead rock, but a world kept alive by the invisible hands of gravity. Everything changed in 1979 when the Voyager spacecraft finally reached Jupiter. Its cameras, sharper than any Earth-based telescope, sent back the first true images of Io's surface, and the results were stunning. Instead of a gray, cratered wasteland, they found a world of vibrant yellows, reds, and whites, a landscape dominated by sulfur and volcanic activity. One photograph captured a massive plume of gas and dust erupting hundreds of kilometers into space. It was the first time an active volcano had been seen beyond Earth. Suddenly, all the old mysteries, the flickering brightness, the infrared heat, the radio bursts, made perfect sense. Io was the most volcanically active body in the solar system. The haze wasn't a lens flare, it was volcanic gas. The shifting brightness was the result of fresh lava and sulfur frost constantly resurfacing the moon. This violent geological life is fueled by a remarkable gravitational arrangement known as an orbital resonance. Io is locked in a rhythmic dance with its sister moons, Europa and Ganymede. For every orbit Ganymede completes, Europa completes 2, and Io completes exactly 4. This mathematical lock means the moons are constantly tugging on one another in a predictable pattern. These small, repeated gravitational nudges prevent Io's orbit from becoming a perfect circle. Because its path remains slightly elliptical, the distance between Io and Jupiter is always changing, causing the planet's gravity to squeeze and release the moon with every revolution. This constant physical deformation generates an immense amount of internal friction, turning gravity into heat. Without this celestial resonance, Io would likely be a cold, frozen sphere. Instead, it is a world of molten lakes and towering plumes, forever reshaped by the invisible forces of its neighbors. The delicate balance between Io, Europa, and Ganymede is more than just a coincidence, it is a grand rhythmic cycle that repeats every 7 days like a cosmic clock. This alignment, known as the Laplace resonance, ensures that the gravitational pulse between these moons reinforce a stable pattern rather than tearing the system apart. In many orbital systems, small changes or tugs can accumulate over time, leading to chaos, instability, or even collisions. However, the 1-2-4 resonance of these three moons acts as a self-correcting mechanism. If one moon begins to drift, the gravitational influence of the others gently pulls it back into its proper place. This stability allows the three worlds to evolve in vastly different ways. Ganymede remains a giant, icy fortress showing signs of ancient activity. Europa hides a potentially life-sustaining ocean beneath its frozen crust, and Io, being the closest and most fiercely tugged, endures intense internal heating that manifests as a surface of fire unlike anywhere else in the solar system. As these moons formed and migrated outward through tidal interactions with Jupiter, they became locked in this gravitational embrace. Once established, the system became self-perpetuating, preventing the moons from drifting into new, dangerous positions over billions of years. While similar resonances exist elsewhere in the solar system, such as between Pluto and Neptune, the interaction between Jupiter's inner moons is the most famous and powerful. On Io, these effects take the cold stone of space and forge it into a world of constant eruption. Yet, gravity is not the only invisible hand at play in the system. Jupiter possesses one of the largest magnetic fields in the solar system, an immense shroud that extends millions of kilometers in every direction. Driven by the planet's rapid 10-hour rotation and its metallic hydrogen interior, this magnetic engine creates a relentless environment of charged particles. Io does not orbit through a vacuum. It carves its path through a dense sea of ions and electrons known as a plasma torus. As Io moves through Jupiter's magnetic field, it acts like a massive conductor in a generator. This movement generates a staggering voltage, driving a powerful electrical current that flows through Io's atmosphere and into the surrounding space. This connection, known as the Io flux tube, creates a glowing umbilical cord of electricity that links the moon directly to Jupiter's poles, triggering brilliant auroras that are powered not by the sun, but by Io itself. These currents also exert an electromagnetic drag on the moon, acting as a subtle magnetic brake that whispers against Io's orbital motion. While gravity is the dominant force, this electromagnetic tension performs a silent, perpetual tug-of-war, minutely refining the moon's balance and rotation over millions of years. The interaction is so profound that Io is constantly losing mass to the Jovian magnetosphere. Volcanic gases, primarily sulfur and oxygen, are stripped away and ionized, feeding a giant donut-shaped ring of plasma that circles the planet. This creates a feedback loop where Io's volcanoes nourish the magnetic field, while the magnetic field, in turn, shapes the environment of Io's surface. This complex dance of energy, current, and magnetic pressure gives Io a dual identity. It is both a satellite and a giant electrical conductor. Even if gravity were to vanish, the signature of Jupiter's magnetism would remain written in the motion of every particle on this moon. It seems almost impossible for a moon to remain geologically active for billions of years without its own internal fuel, but Io defies the odds. Its energy budget is not a dwindling inheritance of heat from its formation. Instead, it is a continuous generation of energy. As long as the orbital resonance with Europa and Ganymede persists, the tidal friction will continue to pump heat into Io's silicate mantle. It is the solar system's most efficient engine for converting gravitational energy into thermal power. While other worlds cool and freeze as their radioactive elements decay, Io remains rejuvenated, its crust constantly broken and remade by the stresses from below. Io's journey tells us how worlds can stay alive without conventional energy sources, offering a blueprint for understanding distant exoplanets in tight orbital systems across the galaxy. This concludes our journey into the restless heart of Io. Thank you for listening, and may your dreams be as vast as the cosmos. Have a wonderful day, and we will see you next time.